Good morning, students. Today we have some student presentations. First of all, Sumaya will be presenting angular dispersion and dispersive power of lens. And after her, it will be Khadija who will explain to us how ray diagrams are drawn in lenses and how the images are formed. And then Muhammad Zaman will derive a relation between the object distance, image distance, and focal length of a lens. So I will request Sumaya to start the presentation. I will share your work. Yes, Sumaya, you can do the presentation now.
Okay, teacher.
Can you all see the slide, the shared document? Can you see?
Yes.
Okay.
So, Assalamu alaikum everyone. Today I will discuss about angular dispersion and dispersive power. Angular dispersion. The deviation between red and violet color is called angular dispersion. When a monochromatic light passes through a thin prism, then the deviation of that ray will be gamma equals to mu minus 1 into A. This equation comes from deviation of light ray in the thin prism. Here, A stands for reflection light of the prism, mu stands for reflective index of prism due to that color of light. Now, if white light is incident on a thin prism, it is split into 7 colors and deviation of each color is different. If the deviation due to red and violet color are respectively gamma R and gamma V, then gamma R
Sumaya,
equals to mu.
1 minute.
Yes, teacher.
The deviation is represented by delta. So this is delta.
Okay, teacher, delta R and delta V, then delta R equals to mu R minus 1 into A and delta V equals to mu R minus 1 into A. Here, mu R and mu V are respectively indices of the material of the prism with respect to red and violet color respectively. So here, angular dispersion, gamma of gamma V minus gamma R equals to, teacher, it is gamma, no?
It's delta, deviation, right?
Yeah, delta V minus delta R.
Small letter
We know
delta.
okay, we know delta V equals to A into mu V minus 1 and delta R equals to A into mu R minus 1. So here we multiplied A into mu V mu V minus 1. So A mu V into minus A mu R plus A. So minus A and plus A will be cancelled out. The remain will be A mu V minus mu R. So here we can see the angular dispersion depend upon the angle of the prism and the nature of prism material. The prism of different materials produce different dispersion. Now dispersive power. The deviation power of prism is the ratio of angular dispersion to the deviation of the mean ray. We know dispersive power equals to omega equals to delta V minus delta R by delta. Here delta V minus delta R stand for angular dispersion and delta stand for angular dispersion for mean ray. Now, if A is the angle of prism and mu V, mu R and mu R respectively indices at the prism material for violet, red and mean ray respectively, then delta V minus delta R equals to A into mu V minus mu R and delta equals to A mu minus 1. So dispersive power omega equals to angular dispersion by angular dispersion for mean ray. That is that is A into mu v minus mu r by A into mu minus 1. Here A and A will be cancelled out and the remain will be mu minus omega equals to mu v minus mu r divided by mu minus 1. Here we can see dispersive power omega at prism depend only on the nature of the material of the prism. Then why is red color used in danger sign? The primary reason why the color red is used for danger signal is that red color is scattered the least by air molecule. The effect of scattering is inversely related to the fourth power of the wavelength of a color. So red color is able to travel the longest distance through fog, rain, etc. Then why does sky look red at the time of sunrise and sunset? The sun is low on the horizon. Sunlight passes through more air at sunrise and sunset than during the day. When the sun is higher in the sky, more atmosphere means more molecule to scatter the violet and blue light away from our eyes. This is why sunrise and sunset are red in color. Finish, teacher.
Okay, so uh, she made the notes very clear. So I will also share this in our WhatsApp group. Go through her notes, and if there is any doubt, you can ask her. Is the concept clear to you?
Yes, teacher.
Okay, so I will stop sharing this. And who is the next person? Khadija. So, Khadija, you can share your screen and start your presentation.
Teacher, can you see my screen?
Yes, yes.
Assalamu alaikum everyone. I'm Khadija and today I will be talking about ray diagram formation in lens and the image formation. So what do you mean by ray diagram? A ray diagram is a representation of possible paths light can take to get from one place to another. So there are usually we use ray diagram for formation of images. There are at least two rays, then only we can find an image. So usually we can see there are many rays being directed in this lens. This is a convex lens. This object is directing many rays like in this parallel to the principal axis and in many other places, but we will not consider all these rays because it will make our ray diagram very tough. So we usually consider three rays in concave and convex lens. They are the rays parallel to principal axis, rays passing through focus, and the rays passing through optical center. So in first case, ray parallel to principal axis after refraction passes through the focus in convex lens or appears to come from focus in concave lens. This is the convex lens and we can see this ray is parallel to the principal axis, and after refraction it is going through the focus. And this is the concave lens in which the ray is parallel to principal axis, but as it is going, but we feel like it's emerging from this principal focus. This is the second case. Here, the rays passing through focus will become parallel to the principal axis. Here we can see this ray is passing through the focus, but after refraction it goes through parallel to principal axis. And here also same happens. This it is we feel like it is directed towards the principal focus, but and after refraction it is passing through parallel to principal axis. Mm, this is the third case. Here rays passing through optical centers go straight. Here we can see this ray is going straight through the optical center. In this case also the same happens. The rays is going straight towards the optical center. Okay, an image is defined as the collection of focus point of light rays coming from an object focus points actually made by converging rays. Rays create a real image, and diverging rays makes a virtual image. Now we'll talk about the image formed by a convex lens. So here we can see this is the convex lens, and this is the principal focus BOF2. AB is the object, and O is the optical center. F1 and F2 is the principal focus. So we can see a ray. This object is directing a ray towards this optical center, and it goes straight. Another ray is parallel to the principal axis. After refraction, goes through the principal focus, and they meet at this point. These two rays, the one going through optical center and the one after refraction goes through focus, they are meeting at this point A dash. So if we draw a line perpendicular to B O B dash, we will get this image B dash A dash. This is our required image. So the shape, size, and type of the image formed in convex lens actually depends on the position of an object. If we keep this object in between focus and optical center, there will be a different image formed. If we put it in between f2, double of principal focus and focus, we'll get another image. Its size shape will depend on how we keep where we keep our object. um, this is the Now we will be talking about the image formed by a concave lens. Here, this one is our concave lens, and BOE is our principal focus, AB is the object, and F1 is our principal focus. We see a ray is directed from this object towards the optical center, and it is passing straight. Another ray which is directed parallel to the principal axis. This line is parallel to the principal axis. After refraction, it seems to emerge from this point. This F1. F1 is the principal focus. As this both this ray, like the ray passing through optical center and the one after refraction goes this way, they are divergent, they won't meet. So we will extend them backwards, and we will see that they're meeting at A dash. So if we draw a line A dash B dash parallel to the object AB, this is our image. So the in a concave lens, the image is usually erect, virtual, and smaller than the object in size. That's it. Teacher, finish. Teacher.
That was a very good presentation, Khadija. The explanation was very good, and the slides were also excellent. What about others? Did you get the idea clearly?
Yes, teacher.
Okay, so Mohammad Zaman, now you can start your presentation.
Okay.
You can unmute yourself.
So teacher, I'm gonna start now. Is the video clear?
Real time.
Okay, assalamu alaikum. I'm Jaman, and I'm gonna talk about some of the quantities related to geometrical optics. So first, I'm gonna make a relation between object distance, image distance, and focal length. Okay. So in case of lens, the relation of an object distance and focal length and the image distance is 1 by v plus 1 by u equal to 1 by f. We learned in class 9. Okay. And I'm gonna derive it at the last. So we have to understand the quantities. F is the focal length. F is the focal length of the lens. U is the distance of the object from the optical center, and V is the
Excuse
distance
me.
of the image from optical.
Excuse me, Zaman.
Yes.
Irfan, mute yourself.
Sorry, teacher.
So U is the distance of the object from the optical center, and V is the distance of the image from optical center. And I'm gonna talk about linear magnification. Linear magnification means the ratio of the length of the image to the length of the object is called linear magnification. So the general formula of linear magnification, and we denote linear magnification by small f. I mean small m, sorry. So small m equal to L prime by L. L prime is the length of the image, and L is the length of the object. So I'm going to give an example. This is an image formed in convex lens. AB is the object, and A prime, B prime is the image of the object. So the linear magnification of this object AB is M equal to A prime, B prime by AB. Okay, that's another formula for linear magnification, that is M equal to minus V by U. V is the distance of the image from the optical center, and U is the distance of the object from the optical center. And here negative sign means the image will be inverted and real. And we know when we use convex lens, we will get inverted and real image. And from my next quantity is angular magnification. For understanding angular magnification, we have to understand what is visual angle. The angle subtended at the eye by the eye. The angle subtended by the eye to the object is called visual angle. So I'm gonna give an example. See, suppose this is an eye. I know it's not looking like an eye, but just suppose. And this is an object. Okay, so the angle in our and our eye, the angle will formed will be like this. This is the visual angle of this object in our eye. And if we take the object closer to the eye, then it will be like this, and the angle will be much bigger. So when the object is when the object is much nearer to our eye, the visual will be more, angle will be more. Okay, then angular magnification. And for okay, the ratio of the visual angle, first of all I have to mark this one highlighted. Visual angle produced by the image and visual angle produced by the object. So the ratio of visual angle produced by the image and the visual angle produced by the object at the eye is called angular magnification. First, when image is formed, when we use instrument like lens, and for angular magnification we will use like instrument like telescope and microscope. And the general formula of angular magnification is beta by alpha. Beta is when suppose for a situation we are seeing a moon. So when we see normally with our eyes without using any instrument, the angle will be created in our eye is, let that is alpha. Okay. And when we see a moon using telescope, the angle will different. I mean the visual angle will be different, and let take that angle is beta. So the angular magnification will be m equal to beta by alpha, and we will use capital M obviously. So difference between both magnification, I mean what's the difference between linear and angular magnification, and when we will use which magnification. So let's take the same situation, we're seeing a moon, and this time we will take the linear magnification. So linear magnification is small m divided by L prime by L. So this time we're seeing the moon using a telescope. So when we see a moon using telescope, the size of the image will be maximum up to, I mean, almost 4 to 5 centimeter. Okay, let's write 5 centimeter. And L is the size of the object or length of the object. Now here's the twitch. I mean, what is this object? Object is the moon, right? The size of the moon means actually the size of the moon. It the radius of the moon is around 1,700 kilometers. So if we use this formula for finding the magnification, we won't get, because anything divided by that much bigger quantity will give you zero. So this magnification will give you a wrong percentage, so you have to use angular magnification in this case. So I'm left with two graphs, the graphs of u and v. So first of all, the u versus v graph, and then u 1 by v versus 1 by v graph. So in the first graph, u versus v, we always get a hyperbola. I mean, why hyperbola? So I'm gonna draw that graph again. Sorry for the drawing. It's really bad, I know. So in the x-axis, we're taking the distance of the image, I mean, distance of the object from the optical center. So this is the way u, and this is the v, because the distance of the image from the optical center. So the object can be put any, I mean, kept any place. First of all, I'm gonna keep it infinite. I'm gonna mark some things. This is the focal length, and this is 2f. I mean the radius of curvature. And in this line, this is the f, and this is the 2f. And for an, I mean, a lens have a definite focal length, and it's constant for this type of lens, for a simple lens. Okay, so first I'm gonna keep the object at infinite. So infinite may be somewhere here, and that when the object is infinite, the image will form at principal focus. So this is the principal focus, and the infinite will be somewhere here. I'm drawing the point here. Then when we keep the object nearer to another, we will keep the object now nearer to 2f, but not 2f, nearer to 2f. So it will be somewhere here. And when an object is on radius of curvature, is more than radius of curvature, the image will form between of principal focus and radius of curvature. So if this is the case, then this next point will be somewhere here. And now the another situation that we are going to keep the object on 2f. So the object image will also be formed at 2f. So it will be somewhere here. And the last one, we're going to keep the image on focal distance, I mean principal focus. When the object is on principal focus, the image will form at infinite. So this is the principal focus, and the infinite will be somewhere here. So when we just match these lines, it will give a parabola, a hyperbola type. Okay, so next equation, I mean next graph, that is 1 versus u, 1 by u versus 1 by v graph. And is straight line, it gives the straight line which cuts at x-axis and y-axis. And why that happens, let's see. Suppose this is the graph, it is 1 by u, and this is 1 by v. It's on y-axis, and this is on x-axis. So we learn the formula relation, right? That 1 by u plus 1 by v equal to 1 by f. And the focal length will obviously constant for this one. Suppose this is the focal length 1 by f, and this is also the focal length 1 by f. So this, we took 1 by u on x-axis, so let's take this x, and this is 1 y-axis, so x plus y equal to 1 by f. So first of all, I'm going to take x equal to 0, x equal to 0, so we will get y equal to 1 by f. So this is the point I got first. And I'm going to take x, y equal to 0, then we will get x equal to 1 by f. So you got 2 points. Now if I draw a straight line around it, we will get a straight line that cuts through at x-axis and y-axis. Okay, so the last derivation of this famous formula, this is again the same image formation of an object in convex lens. So I'm gonna derive the same formula, that is 1 by u plus 1 by v equal to 1 by f. This is the formula. So I'm gonna take, first of all, I'm gonna take triangle LOF2. This is the triangle LOF2, and F2 B prime and A prime. F2 B prime A prime. This is now these two are similar. Why similar? I'm gonna say, wait. Suppose I draw the same two triangles here. It is something looks like this one, right? This is L, this is O, this is F2, and this is B prime, this is A prime. So this both of these angles are equal, and then this 90 degree, this is also 90 degree. So we can say that this angle is also equal. When the three angles of two triangles are equal, we can say they are similar, and when they are similar, the ratio of their sides will also be equal. Okay, so as I'm considering the first two triangles LOF2 and A prime B prime F2, so this side of this triangle LO by the A prime B prime, because these both sides are I mean similar to, this is the, maybe if we consider this the opposite, then we will consider this one also opposite. So A prime B prime equal to, the other side is OF2 F2, then F2 B prime, F2 B prime. Okay, so I'm gonna say this from B to O, this AB is the object, right? So this will be the U, because this is the distance of the object from the optical center, and OF2 is the focal distance, focal length. So we will consider it as F, and OB prime is the distance of the image from the optical center, that is V. So this will always this will be V minus F, because if we add this one, we will get V. So it will be V minus F. So what is OF2? OF2, that's F, right? Because that's the focal distance or focal length, and F2 B prime, that is V minus F. So B minus F. Let's take this one, equation 1. Okay, now we'll consider another triangle, that is ABO. I'm gonna highlight this one, ABO, then O A prime B prime, this triangle. The same formula goes for this one. These two angles are equal, then this is also 90 degree, this is also 90 degree. So this angle and this angle will be equal. So when the three angles are equal, both of the triangles are similar, and when they are similar, their sides ratio will always be equal. So from this triangle we are taking AB and A prime B prime, and this side BO or OB and OB prime, OB prime. Okay, so another thing is that AB, see, and AB is parallel to LO, and AB, so, and we can say AB equal to LO. So in case of AB, I'm writing LO by A prime B prime equal to, it will be same O, okay, sorry, it will be OB prime. Oh, what is OB? OB is the U, the distance of the object from the image, from the optical center. So in case of OV, I will write U. And what is OB prime? OB prime is V, because it's the distance of the image from the optical center, V. Okay, so this is another equation, equation 2. So if we compare these two equation, see, LO A prime B prime, this is also LO A P prime B prime. So we can say this one equal to this one. It's a normal formula. So I'm gonna write F by V minus F equal to U by V. Okay, so if I multiply, cross multiply, VF equal to VU minus UF. So dividing both sides by UVF. So it will be VF by UVF, VU by UVF minus UF by UVF. So VF, BF gone, VU, UV gone, UF, UF gone. What we remained? This 1 by U equal to 1 by F equal to minus 1 by V. So if we take the minus V that side, it will become 1 by U plus 1 by V equal to 1 by F. Hence I derived this one. So up to this was my presentation. Thank you.
What do you think of the presentation? Students, what do you think of the presentation?
It
Sorry,
was
teacher, it
very
was
clear.
forced.
It was excellent.
Excellent.
Mama Zaman, you made a very clear presentation. The
Yes.
explanation was excellent. So thank you very much. And I hope it is clear to all of you. Please go back and read the textbook as well. So because it is very important that what you learned here, you have to go back and learn in the textbook as well. So I was recording this and I will upload this presentations in YouTube and share the link with you. Now, I also want to remind you something. Tomorrow, 10th November is the last date for the submission of assignments. So remember, go to the Google Classroom and submit your assignments either today or tomorrow itself. There are 4 creative questions and you have to do that. So who all are the presenters for tomorrow? Mariam Sultana and Rifat will be presenting the determination of position, nature and size of the image formed by a lens. And Aisha will be presenting the power of lens. Are you ready? Mariam Sultana?
Yes, teacher.
Yeah.
And Rifat?
Yes, teacher.
And then Aisha.
Yes, teacher, I'm ready.
Okay, okay. So thank you very much. We will see tomorrow. I am going to end the meeting now.